Hello everyone. I am Ankita working as a software engineer and we already started a series on AI and we'll be teaching from LLM to building multi-agentic workflows using MCP. So let's get started. In the last video, we learned about the input tokens and embedding, after that outputs as well. But still we didn't cover the transformers. So in this video, we are going to cover the transformer part as well. So what transformer is doing. As of now, if we'll see, the transformer is a mechanism or architecture behind most modern LLMs. If we'll understand this, then we'll understand how this LLM is working behind. So this idea came from the famous research paper, that is attention is all you need. So we'll go and see for that paper. Yeah, so this is attention is all you need. This is launched by the Google brains and Google researchers are there. So these members launched this research paper. In this research paper, we got to know about that transformers. Okay, so if you'll see here, there is a background, model architecture, encoder and decoder concepts, and then attention is there, multi-head attention, application of attention in our models, and many more things are there, right? So let's get back to the our part. Yeah. So this paper was launched in 2017. And after that, we got to know about this transformer. Okay, so before moving into the transformer, we'll know before transformer how things were working, right? So before transformer, what happened is it that models are not able to handle the long sentences. If we'll provide some long sentences, models will not know. They'll not able to handle all these things. So suppose, for example, if we have the boy who was wearing a red hat and carrying a heavy blue backpack while walking his dog in the rain and sat down, right? So if models will go read this word, what it will do, it will go one by one from left to right. By the time it will reach to the word sat, they often forgot that the subject was the boy. This is called vanishing gradient problem. So before it don't know, if it will go to the end of the sentence, and that is a long sentence, right? So it will forgot, okay, what is that before we are here now, but it don't know what is before, right? So that problem is called as a vanishing gradient problem. And now what transformer is doing is they are using something called self attention. Instead of reading that in all the order, the model look at every word in the sentence simultaneously. So will not vanish that information, or that information will be captured, right, by the model. So that was the issue before transformers. Now, and models were very slow because it will be sequentially going by one, right? It cannot process the 10th word until it will reach by first, second, third, and till 10th, right, till ninth, and so on. So that is very slow process because it's going sequentially over there, right? And then context confusion also. So for example, that I went to the bank to deposit money and I sat on the river bank. But here that older models might give that bank is the some different information, right? So what it will do is the same mathematical representation in both cases, that will missing the context. That context will be missing. It will not be able to understand what this bank means is, and sorry, yeah, and what this bank means is, right? So it will confuse over there. So what happened after transformer? When transformer came in picture, that is a very faster one, and it will understand the context in a better way. And that models like ChatGPT, Gemini, all this will be powerful because of this transformer concept. Yeah. So we'll have attention mechanism. Just now we saw in the paper, right? We have some attention, self attention, multi attention, right? So we'll go one by one. So what is this attention mechanism? When we are processing a word, the model looks at other relevant words in the sentences. So self attention helps a model to understand how words in a sentence are related to each other, how they can relate each other, right? So it will help that self attention will help them, and it allows the model to look at all words at the same time and decide which ones are important for understanding the meaning of each word. So that model should know in the sentence what are all the words are there, how they are related with each other. So for knowing that, model needs to understand all these parts. So self attention helps the model to understand these things, right? For example, the cat sat on the mat because it was tired. What does it refer here? That model learns it could be a cat, not a mat, right? So because of this self attention, it's very easy for the models to understand these things. Okay, so now how these attentions work. So as we already know, word will be converting into a numbers or vectors, right? After that, each word in a sequence is mapped to the three parts. We'll have three parts. If you'll see here, one is query, then key, and then value. So we'll have three parts. Query means what this word is looking for. Key means what this word offers. Value means actual meaning of these information. Okay, if we'll see the real life examples, when we'll be searching on the Google, right, we'll be giving some query. Query means what we are searching for, right? So our question is a query for the Google search engine. Now we'll have keys as well, right? So for key, all the available content, okay, whatever the content is available in the Google, that is the key for that model. So our key or questions, Google compare with all the pages, whatever the relevant pages is available in the Google, right? It will compare all these things, and value means actual information. Whatever the websites we are getting, right, with our query, it will fetch all the keys. In the keys, maybe if we'll ask what is model, so wherever model is there, according to that key, it will search all the pages and we'll get the relevant pages. And after that, when we'll get the relevant pages, we'll be going inside one of the page and we'll see that content, right? So that is the values for that, or actual information we are getting here, right? So we'll match query with the keys and we'll get the relevant values for that. So how we'll not go in depth of this one, but we'll see attention is pure computed, right? So we have this formula, attention QKY equal to softmax. It will going for the softmax operation. Okay, so we'll just know how attention is going to be calculated. We do not need to do these things, but still we'll be aware about this formula. Okay, so this is based on the dot product between these queries and the key. Now next thing is multi-head attention. Instead of doing attention once, transformer do it multi times in parallel. It will go parallel and it will do the attention, right? So instead of doing attention once, transformer do it multiple times in parallel. This helps model to learn different relationship, means we'll have grammar as well, meaning as well, and other context as well. So parallelly it will go and understand all these things, what the things within this particular, within the particular sentence, right? It will go and understand all these things. So each attention will capture different relationship or pattern in the data. In self attention, we will have one QKV, but here we'll have more QKV, like as Q1, Q2, K1, K2, right? Like this, it will have one head. That yeah, we'll see this attention, right? So similar way, we'll have more attentions over there. So one attention is Q1, K1, V1, yani query 1, query, key, and value. So we'll have 1 1 1. And if we have another head, then we'll have another Q2, K2, and V2, right? So this will be more in the attentions, will be more in the multi-head. So it will understand the other context as well. It will not go only for the one context, because inside that, as a human, we can understand, okay, this means that particular thing, but we don't know. Okay, as a computer, it don't know, so we have to provide these things. So all these contexts, it will gather together. For that, we will be using the multi-head attentions. Now each head have a different weight, learn different features. So if we'll be getting we'll be giving our question, right? But if Google search engine will search all these things, it will go to the one layer and it will just figure it out, okay, what we are asking, what could be the keys, right? So that keys will be the another weight for the or another parameters for their search engines, right? So like this it will work. So same here also, each head will have different weights. For head 1 will have different number of parameters. When it will come over from the head 1, it will have some another number of parameters. Weight is nothing as a parameter, so we'll have different number of parameters and it will learn different features, and after that at the end we'll be getting the responses. Okay, so now, yeah, we'll move to the transformers. So here, as the problem before transformer was, it was searching in the sequentially, right? So now that problem is not there. It's going for the parallel work. So it will parallelly search all the words over there. And this is a type of a neural network architecture that excels at processing sequential data, most prominently associated with the LLMs. Okay, so if you'll see here, it's mentioned as a transformer is a neural network that understands relationship between words using attention. So it is using attention rate, what we learned before, multi-head attention and attention rate. So using that, it will understand what are the relationship between the words we have, right? And takes embedding as an input. So as we already learned in the last video, that we have some inputs that will be converted into tokens, then it will go for the embeddings. So takes embedding as an input, so it will take embedding as an input and understand relationship, whatever words or sentence we send, right? So it will understand the relationship between them, and after that it will produce the context aware output. Okay, so it will know what is the context now and it will generate the output for us. And the key behind all these things is the self attention mechanism. Okay, so we'll go for the transformer architecture now. So suppose if we'll be asking, hello, how are you? Okay, it will, and we want to convert this into the Hindi language. So it will go for the transformer, or we can say LLM model, and we'll get the namaste, aap kaise ho, right? So we'll get that answers over here. So how this is going to work, or how this part is, that architecture is there, we'll see. Okay, so there are two main parts inside the transformers. First thing is encoder, another the part is the decoder. So we'll have encoder and decoder. If we'll give or provide some questions to the models, it will go to the encoder, and after that it will move forward to the decoders, and at the end we'll get the outputs. So we'll learn one by one what are these encoders and decoders are. Okay, so encoders means understand the input sentences. Whatever the input we provided, right, it will understand our sentences. And decoder, what it will do is it will generate the output from that sentences. So we'll go one by one and we'll understand the encoder and decoder in depth now. So what is this encoder? Encoder will get the list of vectors as an input. So as we already know, when we'll have some input that will convert into the tokens, and after that it will go for the embeddings, right? Embedding is means that vectors will get that data in the vectors format. So after embedding that, the process of transformer will came in picture, right? So in bit after, so when that data will be going to the transformer, that transformer will get the list of vectors as a input, right here. So when we'll send hello, how are you, encoders will be getting that data in the form of vectors. So self attention look the other words in the sequence and capture that context here. So what will happen is multiple encoders and decoders stack will be there. It's not like that we'll have only one encoder and one decoder. It will have multiple number of encoders are there, and multiple number of decoders will also be there. So when we'll send some data, it will go to the one encoder, and after that it will pass to the another encoders, and it will go till the n number of encoders, and after that that decoding process will start. So it will go to the one decoder, another decoder, right? So one by one these information will be going to the decoders, and at the end we'll be getting the output or our responses from the models. Okay, so why we'll have multiple encoders and decoders. So what will happen is, if encoder 1 will be giving some output, so suppose it's just understanding the basic relationship between the words, what will be the basic relationship will be between the words, it will just understand it. And if it will go to the another encoder, it will correct our grammatical errors. And third one, it will understand the or resolve the meaning of these words. And fourth one, maybe it will go and search, okay, what the other related context could be here. So like this, it will one by one it will go, and it will perform some another operations. These encoders will not perform the same operations. So if we'll have one encoder, if will be going to the another encoder, so there will be some weights, or there will be different parameters will be there. It's not like that if we'll come from hello how are you to the first encoder, whatever the list of vectors went to the first encoder, it will not same list will go to the second one. So we'll have some different list over here. So different list of parameters will be going to the another encoder. Okay. uh, and this is similar way for the decoder as well. So it's a stack of decoders, so one by one it will go to the, it will get different kinds of responses, and it will enhance that response, and at the end will be getting the output. Okay, so this is the overall architecture of the transformer. So in this we'll go one by one and we'll understand what all these parts here is. So if we'll see here is, we have encoder and we have decoder. So multiple stacks of encoder will be there. Here I just mention it as 2. So but there can be a n number of encoders and n number of decoders will be there. If here we mentioned it as a 2 encoders, right? So decoders will also be the same. We have 2 encoders, encoder 1 and encoder 2. Similar way we will have decoder 1 and decoder 2. And we'll be going inside what is this inside the encoder is, and what the data inside the decoder is. So we'll go one by one. So as we already know, we'll give some input just like as any questions or our queries, and then it will go for the input embedding. So it will convert the data in the vectors, and after that we'll add the positional encodings on this one. When we'll add the positional encoding, after that that data will go to the encoders. So inside encoder, that self attention mechanism will come here, right? So it will look the other words in the sequence, or it will capture that context, what could be the context for the other words here. Then it will process the feed forward network, right? So whatever the information it will come, it will go to the feed forward neural network. So feed forward neural network, what it will process each word individually, that all the words whatever the output is coming from the self attention, it will go to the feed forward neural network, and it will individually refine its meaning and make the representation stronger. So when it will come out from the feed forward neural network, that will be the stronger output from that. Okay, for example, if we'll see the cat sat on the mat because it was tired. Here, what FN will be do, or we can say feed forward neural network will do, after self attention, it will be like it plus a strong cat information, right? So what it will do after self attention, we will get it. Okay, it is like, okay, we'll have cat information and mat information also there, right? Because the cat sat on the mat, so we'll have cat information, mat information, and it also. Okay, so this is a mixed, or this is a raw context, not the final understanding here, right? So what will happen is, feed forward neural network, it will make all this information and process it individually. After an FNN, what we'll get is, it refers to the living cat, subject of being tired. Okay, so it should know now. After this part, we'll know, okay, the cat, that it means cat. Okay, it is referring to the cat, it's not referring to the mat. So because of this feed forward neural network, we'll know these things. And in between self attention and feed forward neural network, or everywhere, right, we'll see add and normalize processes also there. So what it will do is, it will add the original input to the output. So if we'll see here, whatever the data is coming from the after positional encoding, that input is also going to the add and normalize layer. So it's knowing, okay, what input we provided, it knows about that part. So we'll keep this original meaning same. So that add and normalize layer, it will have our inputs as well, so it knows what is the original meaning of, or our original ask was there, right? So it already knows about this. And model will not forget the original information because of this add and normalize process. So in normalize, what it will do is it will clean the value, so next layer will have clear information, so next layer will not get the messy numbers. Okay, so it will just normalize these parts which will be coming from the self attention layer or from the feed forward neural network layer. So that's what it's going on. First we'll get the input, it will go to the add and normalize process also, and now we already know why it's going to the add and normalize. And what will be the output from the self attention, it will also go to the add and normalize layer, and then after that it will go to the feed forward neural network layer. And again from here we'll be going to the add and normalize layer, because we want our input as it is, so model will not forget okay what input we provided, right, to the model. So it will know about these things, that's why we are again sending that input. And now when add and normalize will be done, so encoder one part is done, it did its process, and same information what will be the output from after the add and normalize, it will go for the another encoder, that is encoder 2, and we'll again same layers will be there, self and attention, add and normalize, feed forward neural network, add and normalize again, right? So same way encoder 2 also behave, there is nothing different, but for them that input parameter is different, so they'll do some another task, but the layers are all same. If we'll have another third encoder also, that layers and their mechanism is same, but they'll have some different kind of weights. Now we'll move forward to the decoder parts. So if we'll see here in the decoder, there is one extra layer, that is encoder-decoder attention, except that all the layers of encoders are same. Okay, so what decoder will do? Decoder will generate the output sentence one word at a time by using the input meaning and the word it has already generated, right? So it will have the input, and now it, whatever the information is there, it got from the encoder, and now decoder needs to generate the output. So what it will do, it will generate the output sentences, and it will go one word at a time, it will not do many things, so it will go one word at a time, and it will also use our input meanings and words it is already generated. And it will have masked self attention, it's not a normal self attention, it is a masked self attention. Masked self attention means it will not see the future text, it will, for now we know, okay, it will, if we'll saying okay the cat, so first it will see the, okay, so it will first see okay we'll have the, and we'll check for the cat, as of now that self attention is doing, but here it will not see the feature text, it will work for the past test, because if we'll have the, then what could be the next, so we have to see for the past, whatever the past information we have, according to that will make the future information, and it will have input from the encoder. Okay, here we have a cross attention, or we can say encoder decoder attention, this layer we can say as a cross attention as well. So decoder, what it will do is it will look at the encoder output to understand input sentences. So whatever the, if you'll see here, whatever the output is coming from the encoder, that will be going to the encoder decoder attention. So it knows what is the output coming from the encoder and what output it have to generate, right? So it will understand all these input sentences what is coming from the encoder. And this is we already, as we already discussed, this add and normalize feed forward neural network, so it will be behaving same here as well. And after this decoder 1 we'll have decoder 2, so whatever will be input is coming, or output is coming from the decoder 1, it will be going to the decoder 2. And when that decoder 2 process will be done, it will go for the linear, linear mathematical calculation. After that it will go for the soft max calculation, and at the end will be getting the output probabilities. So these models, whatever the information we are getting, these are only the probabilities, because it don't know what could be the actual information. It will go here and there, right? It has the some stored data, and it will go and fetch all these information, and according to that we'll get to know that, okay, it will get to know that, okay, this is the most likely word, so we have to make this as a output. So these are the probabilities it is calculating. Okay, so if we'll see here, right, as we already mentioned, for example, the cat sat on the mat because it was tired. So after self attention, what will happen is it. In this it, what is it? So this is strong a cat information or little mat information. So it did some probabilities and it checked it. Okay, what is the possibility or feasibility here for the it? So is the, it's strong intuition is strong cat info is the main part here, and this mat information, okay, this is the little information, it's maybe it is not applicable. So okay, so after that this raw data it's went to the feed forward neural network, and here it refers that, okay, this is a living animal, it means it refers to the cat. Okay, it's not going to the mat. Okay, so we already discussed in decoder, this is a not a normal self attention, this is a masked self attention. Okay, and this is the diagram from the attention is all you need paper, research paper. Okay, let me check this part. Yeah, so this you can refer it here. So this is the original architecture. So same thing we already mentioned, and here it mentioned as a multi-head attention. So we'll be using the multi-head attention, and we'll have masked multi-head attention, right? So all these it will go one by one to the another layer, and at the end we'll have linear softmax calculations, and at the end we'll be getting our output probabilities. Okay, so what are the places where we'll be using this LLMs, right? So LLMs can be trained on number of tasks. It's not only for one task they are trained, they can do many things. When we'll give a prompt, it will produce a text, video, images according to our prompt. So whatever things we want to do, that LLM will do for us, we need to provide a proper prompt. If we'll give the proper prompt, we can get the text, video, audio, images, whatever things. Okay, if we want to learn something also, it will provide us the information, but we have to write a proper prompt. And it's used in any large complex data which is used to train the LLMs, including programming languages also. So they can help developers to write their codes. So if we'll feed them that any language like as Java or Python, right, they'll be able to help us as a developer. Sorry, it will help the developers to write their code as well. And third one is we can use them for the sentiment analysis like as DNA research, chatbots, online research as well. It will help us to for the analysis as well. And nowadays we'll be using, right, ChatGPT, Gemini, Olama, and big chat models as well, right? So these are the use cases which will be used for the LLMs. And text generation, text summarization, code generation, sentiment analysis, everything, these are the things we can do with the help of LLMs, right? Or in these places LLMs are used. Okay, what are the cons here? So when we'll be asking something, or we try to build a memory for one chat, right, we'll ask some questions, and we'll do some research, right? So it will hallucinate, and the model generate information that is false or misleading. So we cannot 100% rely to the models. We have to know that particular term or scenarios, and according to that we'll decide, okay, whether we are getting the proper information or not. And it will produce output that is unfair or offensive as well. So we have to be more careful if we are searching something over there. And their resources demands are significant. It needs huge amount of training data. For running LLMs we need computational power and energy, and it will raise our cost and environment concerns. So these are the cons for the LLMs. So in the next video we'll be going to learn about the practical thing, right? Because we already know what is the LLM behind. So now we'll go and implement how we can implement that LLMs. Thank you.